Okay, happy 6th week of our metallurgy class. I'll be talking about microscopy and go through a couple examples of microstructures on quality of imaging and also to understand how a microscope works. So looking at an overview, we'll go over the microscope and some of its features. Um, and some of those features it's good to know, especially if you are looking for the best quality imaging. And then from microscopy, we'll look at the different illuminations that you can use and their advantages. And I totally forgot to add the electron backscatter diffraction, but I will talk about that later. So micro what? These are terms that are now should be very regular when you are working with a microscope or taking pictures. So your microscope obviously is going to be the instrument that's capable of producing these images of small objects. And those images that are the purpose why you use a microscope is because everything that you are going to be looking at in phases will be microscopic. And that's going to be anything that is greater than 25 times magnification. The micrograph is the image that is produced. So you will call it a photomicrograph. Don't call it a microphotograph because that means it is a picture that is that you can only see at 25 times magnification. So in this case, you would say it's a photomicrograph of that prepared specimen. And of course, because we're using the microscope, your microstructure is what we are going to be analyzing, and that can only be done using magnifications greater than 25 times. So the instrumentation, there are really two types of microscopes that are used for microscopy, and you have the inverted microscope, and that microscope is arranged in such a way that the line of sight is directed upward into the objective. So this would be an inverted microscope over here on your left. So the objectives are positioned here at the bottom, and all the mechanisms of the microscope are down below, and your image is produced through this hole here. Then you have the upright microscope, which is the opposite. You have the objectives above the sample, and you're looking downward onto your object. I typically prefer the inverted microscopes for the for metallographic observation, and one of the biggest reasons for that is because when you are producing your metallographic mount, you would put your sample face down. So your sample would be face down onto the stage. Okay. When it's face down, because you've polished it, it will have a parallel surface that would be pretty much perpendicular to that light that's coming through the stage. So you will have the best reflectivity. On the other hand, by looking at the upright microscope, in order for this to work, not only do you have to have a polished sample that's flat, but also on the back side of the sample. So if you are not producing samples that are perfectly parallel, like if you plane the sample that has your the surface of your mount that has a sample, then when you put it on the microscope, the backside down, then you're not going to have the best reflectivity. Whereas then on that would not be the case for this microscope over here, because even if it's not on a perfect plane, when you set it on the sample, it will be perfectly perpendicular to that light source. So that's why I preferred the inverted microscopes. Just very easy to use and very user friendly. So looking at the microscope, what are we going to be detailing here? I mean, I'm not going to go through the entirety of why everything is set in such a way, but the important aspect is going to be your aperture, which is this guy right here. It's going to be the field diaphragm, which is right here. You're looking at the vertical illuminator, okay? And we're going to be talking about the objectives, okay? Turns out the objectives are going to be one of the most important parts of this microscope. So looking at these features, the aperture diaphragm is what's in control of the contrast, the depth of field, and the resolution of your imaging. You have your field diaphragm, which allows a certain amount of light in. Then you have filters that you can play with in order to increase or decrease your contrast. And then your vertical illuminator are all those different illumination fields we talked about with dark field, bright field, polarized, and DIC. So the aperture diaphragm is really referenced in optical microscopy as the working diameter of the lens of the mirror. By closing the aperture diaphragm, you are increasing the depth of field, increasing the contrast, but you decrease the resolution. And when you're working in metallography, really the resolution is the most important because you need to be able to identify what the differences between phases. So what do I mean by depth of field? Well, below you can see these three images here, okay? And the depth of field, let me use a blue marker. This one is in focus, but this one is not in focus, and the one on the end, I'll make it red because it is not in focus, right? So that's not in focus. The middle image, this one's not in focus, this one's not in focus, but the one in blue is in focus. And for that last image, that's not in focus, this is not in focus, and you're left with this material. Okay, so what am I looking at? Well, what I'm looking at in this case is the dark gray feature you see on the right. This is a ceramic. C for ceramic. Okay. The center section, this little piece right here, is a tungsten coating. So I'm going to put W for tungsten. Okay. And that last image that's in focus, I'll use red. This is a solder. All right. So I'm gonna put M for metal, but it's a solder. And so what you're looking at is your ceramic material, your tungsten, and your metal solder. Since they're three different hardnesses, they will wear away at different rates. So when you go to look at your depth of field, one will be more in relief than another. Okay, so that's why metallographic preparation, a proper way, is important in this case. How does it work with contrast? Well, with contrast, it's the ability to differentiate the different components within your object by its reflectivity. So the image on the left doesn't have very good contrast, but by increasing the contrast, areas that are more reflective appear brighter, and areas that are not reflective will appear darker. And then you have the resolution as seen here. So like I said, this is probably the most important of the three. And because when you're looking at this top image, you can easily differentiate and measure these the distances between these lines. Whereas when you look at this center image, it's fuzzy. You can't really tell if, you know, if I were to start measuring here to here, is it nice and crisp compared to here to here? And then of course the bottom image is completely just poor resolution. Kind of messed around. You could probably see some of these very faint foggy lines, but it's pretty much one big blur. So an example are looking at these three three images here. Okay, so by looking at these, you have to say, okay, well, which one of these look the best? It's all the same material, and I know that because if I'm looking at, let's see, where's a good image? I know that, you know, you see this and this in the same image, and then you see this. Oh, here we go. This, and this are all the same. So you know it's the same sample. It was just moved to a different location to take those pictures. So what can I say about these three images? Well, it might be pretty obvious, but the one in the center happens to be the one that is blurry, right? So in that case, let's see one of my notes for this guy here. Well, get my pen. So we have poor resolution, which means the aperture was completely closed. Okay. The one in the one to the left, now it's too open. Okay, you might say that image 1 and image 3 are the same, and you really can't differentiate one from the other. But when you're looking at the ferrite within the material, so your ferrite is this phase right here. It's the white phase. This white phase on the left image looks rough, where when you look at the image over here on the right, it looks nice and smooth. You do not see a rough pattern within the ferrite constituent. So out of the three images, the one that has the aperture in the correct location, I'll make it green, is going to be this one out here on the end. Okay, so once again, this one is too open or open too much, and the one in the center is closed. Okay, because when you close the aperture, what it's going to do is it's going to kind of just blur everything out. You lose that resolution, and you can see it a lot right in this region here. So the field diaphragm controls the width of the light that reaches the condenser. Okay, and the condenser is going to be what ends up being your illuminator. So excess light is eliminated, because if you're making it the right size, the right width, then you don't have to worry about excess light producing a glare on your sample, which can also degrade your image quality. So if it's opened up too far, you get scattered light that originates from the sample and also light that's reflected from the other angles, and that will decrease your resolution. So the proper way to adjust your field diaphragm is to, it needs to be centered in the optical path and opened. So when you're looking in the microscope, it's open to lie just on the outside of your field of view. You don't open it all the way up, because that excess light now will create, will lower the quality of your image. Then you have the use of filters. In all reality, you have green, blue, red filters. All of them are used for different methods, but majority of them are to improve contrast and to emphasize special features that are based on material properties. Some of them might also highlight inclusion material if the inclusions under just grayscale are hard to visualize. So the vertical illuminator, the four most common types of illumination are bright field, dark field, polarized, and the differential interference contrast, which is known as DIC. You might even see it as DICM, which is differential interference contrast microscopy. But it's all now on what you're looking at under the microscope. So after you've etched your sample, now you're able to see what that sample is to tell you. And under bright field, it's really just the light hits at a perpendicular orientation, so that's why your sample has to be perfectly flat. If it's rounded, you're going to see darkness on the edges, and it'll be very bright in the center. But this is what you would see for this particular case here. So you see your microstructure. This happens to be a waspaloy, which is a nickel-based superalloy. And looking at this image, you know, you see the grain boundaries, which are the dark features, the dark lines, and which delineate one grain from another. A lot of microscopy really is done in this fashion using bright field. Dark field illumination, using that exact same image, you can see that in the image over here on your left, you see what you would have seen in bright field, and when you're looking at the dark field image, it's the negative of the bright field image. Now, why is this necessary? Why should I look at anything under dark field illumination? Well, with dark field, since it's using light that comes in at an oblique angle, so it's coming in from the sides, what ends up happening is it will reflect off of edges, crevices, anything else that might be, you know, that has a little ledge. And so case in point, when you're looking at this right here, and you compare it to what you're seeing in this image, this waspaloy, since it's a nickel-based superalloy, it'll have an austenitic grain structure, so I should see twin boundaries. Well, the bright field, you do not see the twin boundaries. Okay, they're kind of, the boundary lines themselves are so fine that they're kind of just washed out with the rest of the grain. Whereas in a dark field, they show up really nice. And you can tell, oh, I have twin boundaries within this grain. Oh, I have twin boundaries in this grain. So you could start going through and picking out some of these twin boundaries. There's a small area of twin boundaries here. So now you can start seeing twin boundaries. Whereas if you were to look at this image on the left for the first time, you wouldn't realize that you should have twin boundaries. So polarized illumination, what's nice about this, depending on some of your materials, you may not even have to etch, and it'll produce better results than etching your sample. So this uses an incident light, and the plane is polarized before it impinges on that specimen. So your polarizer gets inserted in this path before it hits the beam splitter, and what it does is it enhances grain contrast, and it works very well with the tint etchants that we talked about in last lecture. But what's nice is the fact that HCP metals, such as these ones here, you don't have to etch the sample to reveal the grain structure. Here's an example. So under polarized illumination, this first image over here on the on the far left is the sample unetched in the as polished condition, no chemicals, nothing on it. That's what it would look like. taking that same sample and applying a polarized look to it, all of a sudden you see a grain structure appear, and that's that center image. So you can see a grain contrast. You can see how these are large grains out here, and these are very fine grains here. Okay. What happens when I etch the sample and view it under bright field? That would be the last image here. So how are you going to tell me about the grain structure in this region over here on the right? Would you be able to tell me what the grain structure is in both of these locations versus what you would have been able to tell me in these two locations? So that's an example of how polarized light could actually help a situation where you would not have received very good results in a etching the sample. And another reason is because you're looking at this dark casing or whatever this was on that outer surface. In polarized light, it still remains. So you could still see how it interacts versus the etchant burning it to where now you would not be able to do any type of microscopy. And the last one is the differential interference contrast. Using this method almost kind of gives you a 3D look at it. And what it does is it reveals the excuse me, topographical or height differences within your sample. So looking at that exact same waspaloy alloy and looking at it in bright field, we have dark field, and now we have differential interference contrast microscopy in the center. Now you can see the true grain structure. It has revealed more twin boundaries than either bright field or dark field. It gives you accurate grain sizes versus bright field and dark field. So this would be a very good example of how differential interference contrast will help with your samples. So it kind of looks three-dimensional, okay, without having to over etch the sample. You can create a three-dimensional look, but this image is fully in focus. If it was over etched, you would see the lower regions of this image would be blurry, and the top regions would have the sharper imagery. So that's how you know that this is not an over etched sample. It has been evaluated using this particular illumination method. So let's look at these objectives. Now that we're here, what do all these numbers mean on the side of an objective? So obviously Zeiss, it's a company that makes objectives and microscopes, but you can look and see, okay, well, the really important parts of this are going to be your magnification, contrast. So 50x means it's 50 times magnification. The 0.90 is the numerical aperture. And this last one, this one here says oil. This is for immersion fluid. So you can actually, instead of just using air, which is the difference between the lenses, you'll have oil that would be inserted in some of these, or you'll have glycerin. Here's some of your examples here: oil, water, glycerin, Or you have a mixture, oil, water, and glycerin. But this black bar shows that it's oil, and it states it's oil here. Okay, because the color of the writing is in black, then it's a standard objective. If it was in red, then you could use it for polarized or DIC illumination. Then let's see what else is important on this that you might want to pay attention to. Really, those are the main things, is what you see right here, and to understand. Okay. So what do I mean by the numerical aperture? Well, the higher your value, the better your resolution. So in images A, B, C, and D on the right, image A has a numerical aperture, that is your in A value, of 0.25, and that does not give me a very good resolution of perlite. But as I increase my numerical aperture going down, and I get to image D, you can see that you can really tell the difference between the interlamellar spacing of perlite. So that would give you the best resolution of perlite. I just threw this magnification, or this formula on here in case you ever needed to identify a magnification. You're given the, or I should say, the angle. But either way, if you needed to find out a certain refractive index to use between air and oil, like I said, you can go in and looking at the images from before, when we were looking at this this value right here. Okay, that's 0.90 oil. So now when you look back at your other image, the oil is actually 1.5. So you could go back and identify the angle difference between that and if you were to have used air. So your image quality. There's a variety of reasons, and for those of you who have not experienced jumping on a microscope yet and taking pictures of your microstructures, you might not have been able to experience some of frustrating times. So listed below are some of the reasons why you'll end up with poor image quality. And the number one is dust and fingerprints on the surface, whether that's on the lens, that's an optical surface, or it's a fingerprint or dust particles on your sample. As a metallographer, the worst thing you can do to somebody after they prepare a sample is touch it with your finger. Do not and never touch a metallographic sample with your finger. Okay, that is, once it is prepared, especially in the etched condition, the moment you put a fingerprint on it, you have ruined the evidence, because the only way that fingerprint can be removed is by going back to repolish, not completely through the entire process, but to repolish and then etch again. And now you're risking, especially if it was a good sample, you're risking bleed out, scratching. What else can you risk? Planing your sample. So the sample after it's prepared is very delicate. The open aperture or the aperture that's too closed. Okay, so once again, if it's too wide open, it washes out the resolution. And then if it's closed, I'm sorry, the opposite way. If it's too open, then what ends up happening is your everything looks like it's in relief. If it's too closed, that means you have washed everything out. You're not going to get the resolution that you want. It's going to look blurry and washed out. A misalignment of the light source is another image quality issue. You'll have some areas that will look brighter than others. Typically, you'll have a bright corner versus a dark corner, and it's because the light is not aligned correctly. Low numerical aperture, just as we saw in the previous slide with the perlite examples. The lower the aperture number, the less resolution that you'll have. Samples being either over-etched or under-etched, a mounted surface that is not perpendicular to the light, and a worked layer of material that has not been removed. So, examples of dust particles, these are not fingerprints. This is perlite, once again. Perlite is just easy to shoot because it gives you that detailed contrast between phases. So the image on the left, this is the good sample, and obviously the one where I've had circled in red are areas that have dust particles or residues on the microscope lens itself. So that would be the bad example. Then when we have the aperture, once again, if it's too open, then you have samples that are in relief, so that's bad. And you can see the ferrite grains surrounding the graphite nodules, which is not something that you would typically see. It looks rough. And then if the aperture is too closed, then it looks washed out. So this is also a bad image. Okay, we discussed that on one of the first slides in this presentation. How about over etching and under etching? Well, everybody would say, well, this is a good image because I can see, you know, the dark phase versus the light phase. Well, true, but when you're looking at it, you cannot tell the interlamellar spacing of perlite. Okay, it's great. You had to over etch in order to reveal grain boundaries between ferrite, but it was bad for what you were able to see for perlite. Then if you under etch the sample, you get really nice perlite resolution, but where's the ferrite grain boundaries? The samples weren't etched long enough to produce those ferrite grain boundaries, which should be somewhere in here based on that previous image. Okay, so the ferrite grain boundaries are not revealed, so it's under etched. Then you have the inadequate preparation of your sample. The image on your left obviously is going to be not good. You have scratches, and disturbed metal tends to etch darker faster. So all this region here where it etched darker is still deformed material. Doesn't give you the true grain structure. Okay, and then you see a bunch of scratches that are that are kind of running through that layer. Then when you have a properly prepared sample, you can clearly identify the grain boundary structure. You can look at the interface between the base metal and this coating. So there's no scratches, no grain pull out. The sample is all in focus. So that ends up being a good image. So tips for when you're going to examine your sample. The first thing to do is to look at your sample in the as polished condition. The reason why it is important to do that is because you are going to look for anything that is already just kind of out of any anomalies that might be already present on the sample prior to etching. So if you look at your sample in the as polished condition, and you just see a bunch of little black dots everywhere, and you go to higher magnification and look at them, well, it's probably particles that are left over from an alumina polishing process or silicon polishing process. And what ends up happening is when you go to etch that sample, those areas that are covered by these particles will kind of block that area from being etched. But the etchant in the end will remove it. So when you go to review it under the microscope, you'll see a bunch of weird looking spotted areas that do not look like they have had enough etchant applied, while everything else around them look like they have an adequate etchant. It's also helpful to determine whether or not you have porosity or secondary cracks that might be hidden after you etch the sample. So after you etch, examine the sample using, if you're going to use high magnifications, you want to perform a light etch first, because if you over etch at a high magnification like 1000x, then the sample is going to look blurry because of the amount of relief on how the etchant attacked your sample. For low magnifications like your 100x, you can just generally just etch it a little longer than a light etch. Of course, you have to know what to expect, know what you're looking for when you're dealing with a sample. If you're working with steel, you have to understand that you're going to be looking for constituents consisting of ferrite, pearlite, cementite, and possibly even austenite, depending on what the heat treatment condition is. Okay, so you have to understand what those structures already look like mentally before you go into the microscope. Make sure you see, make sure when you're doing your examination in the as polished condition and or etched condition, that what you're seeing is real. Going back to those dust and particles on the objective lens, they're going to produce dark spots on your sample, but are those real? Meaning, are they part of the sample, or are they just an anomaly where if you clean the lens, they're gone? Okay. There's ways that you could address that to tell if something is on your sample or not. And worst case scenario, if in doubt and you don't think you did a good job on either the polish or etch process, repolish and etch it again. So here's my fun little slide. It's called What Am I? So what am I? I wonder what material I am. Let's see. Looking over here on the left, and actually in your guys' weekly summary, I want you guys to address this. What am I? I want you to take a second and just give it a guess on what you thought either of these images are. Okay. The image on the left is actually the boundary between the stage and the phenolic resin material itself. So your sample is not even present. Then when you're looking at the image on the right, that is what a phenolic resin looks like. Okay. You can confuse this with steel, especially if it has graphite. So not necessarily steel, but iron, cast irons that have graphite flakes and other inclusion and or slag material from being a casting. But this is actually a phenolic resin. And that's just what it looks like in the cured condition under the hot press. So looking at, what do I mean by representative? Okay. These bottom three images, and this is something else I also want you to address in your weekly summary, is which of the following images would represent a material with the highest carbon content, and which one has the lowest carbon content? Well, to be honest, it's the same material. But if you were to choose an image that has the highest carbon content, then it would be actually the image on the right. Okay, this image over here on the right should have the highest carbon content. The lowest would be the one in the middle. Okay, unfortunately, this happens to be the one with the lowest carbon content is a poor representation of the steel, and the image on the far right that was dubbed as the high carbon content is also a poor representation of the steel. So this is actually the accurate representation of this steel alloy, okay, where you look like you have an equal amount of ferrite and pearlite. If you tell somebody that this middle sample is the representative microstructure of that steel, the first thing they're going to do, especially in pipeline companies, they're going to say the carbon content looks low. Why? Okay. Especially for vintage pipelines where the carbon content is typically around 0.26 to 0.35 weight percent carbon. That would not be a representative microstructure for that. The image on the far right that has the high carbon content, this would be representative of something that looks like, you know, has almost 50 to 60 weight percent carbon content. So that would definitely be a big no-no in the pipeline industry as well, especially nowadays where they're pushing for carbon contents around less than 0.1%. So that's where you need to make sure you take images that are representative of your base material. If you find weird anomalies, that's where you'll go take those images, and then you'll have something to discuss within your report. And now documentation. So in this documentation, one of the important things that you'll need to report is the etchant that's used and the magnification that's used for each of the photographs. So if you're looking up at the top right of this image, I have included a photograph of a Utamet 500 super alloy, which is a nickel-based super alloy. And the example I've provided is what I typically and how I label my figures within a report. So it shows that, you know, figure 6, I have the representative base metal microstructure of the first stage bucket. Okay, I have to identify what I'm looking at and the location of this microstructure, and describe what are you looking at. So in this particular case, this dovetail section is consisted of gamma grains containing both dispersed and grain boundary carbides. Okay, so gamma grains are austenitic grain structures, which are typical of a nickel-based superalloy. And I have dispersed and grain boundary carbides. And the etchant that I used to reveal this structure was Cowling's #2 reagent, also a very typical etchant for superalloys. The magnifications that I used, and I put original magnification just in case, because that was the original magnification I took these images at. So the image on the left is 100x, and the image on the right is 1000x. So that kind of gives you an example of how you would describe your microstructure underneath the figure. Of course, within your report, you'll have a section that's dedicated to just talking about the microstructure, your observations, and how you evaluated them. But when you go to the figures, it's nice to have that description under the figure so they don't have to flip back up to the text in your report and identify okay, what did figure 6 say again? And then look for it in the text. It's already right here. So a lot of the times what people end up doing is they'll just flip to your images, or they'll just look at the summary. And if there's something awkward that they need to address, then they will. But nonetheless, all the documentation is there. So that'll conclude it for the microscopy aspect of it. The microscopes that we have in the labs, I believe, are all equipped with polarizing and DIC illumination, and obviously they all have bright field, and that's what we'll start messing with on Friday, and pretty much from now on, because all of the images that we're going to start taking pictures of in the lab are going to be of samples that are hopefully representative of the topics we will be covering. So next week, I believe it's heat treatment. I'll have to just double check that. I look forward to seeing everybody on Friday for the exam. For those that are not in person, you'll have your online exam that I will be sending you individually. And once again, it'll be a 1-hour timed exam. And that about covers it. So hopefully, if you haven't already worked with microscopes, this kind of gives you a little bit of an insight of what to expect when you go into the laboratory and start playing with the microscopes themselves. Another, excuse me, another kind of rule of thumb: if you're not seeing something in particular when you're working with bright field, before you decide to repolish and etch your sample, try looking at it in the different illumination fields prior to. You never know, you might reveal something that bright field does not. So with that being said, thank you guys, and I will see you on Friday. You guys have a great day.